So, as I told you earlier, today we would finish the discussion on the technologies that cover the cloud computing approach. And as you may know, in the core of the cloud computing approach lies three things. First, it is service-oriented architecture as a basic medium to provide the connection to the remote resources. Second, it is pay-as-you-go approach, and we also discussed this approach while discussing, covering the Amazon Web Services and Elastic Compute Cloud engine. And today we would cover the third approach, the third basic thing that lies in the core of the cloud computing. And without this thing, cloud computing we would not be able to organize it as it works today. It is virtualization. So what is virtualization? What types of virtualization are available right now and most commonly used? And what platforms are mostly used today to organize the virtualization? That we would discuss in our lecture today. So let's go to the virtualization. So first of all, of course, virtualization, right now we would be able to find it almost everywhere. In your mobile phone, in your smartphone today, all applications, either in Android or in iOS, they all are working inside the virtual machines. They work in small containers to organize the containerization of this application and easy deployment. And you also may launch virtual machines on your desktop using such tools as VMware or other virtualization engines. But today we mostly would cover the server virtualization. So what does we mean when we are speaking about the virtualization of servers? So commonly the server that is launched in some infrastructure, it is a big hardware thing. And this big hardware thing, it is mostly organized as a multi-core or multi-processor machine with some relatively big amount of RAM on top of these cores or processors. And this machine works in the service mode. That means that the server listens to incoming requests and provide the responses to these requests. The most common application of the server, for example, it can be a web server. So it listens to HTTP requests and it would give you web pages on these requests. We also know that the same could be applied to REST service. It can be RPC service. It can be some kind of computational server. But in the end, the main pattern is the same. We have multi-core machine with the symmetric access, mostly symmetric access to the RAM, and we want this machine to provide us some services. It also can be some database service, for example. So if we look at this machine from the point of view of the system administrator, then we would see that this server works with some applications. And these applications are these applications that listens to the incoming connections and provide the responses to these incoming connections. So the application servers, it is just a set of applications. And mostly these server applications, they need some very specific environment to work with. So for example, if we want this web server work, then we need some special version of Python. We need some special version of the, I don't know, picture library. We need some special version of compression library. And going and going and going. So this application is not working by itself. It works in the environment. And this environment can be very, very specific for each of the applications, because one server would like Python 2.7 and another server that commonly can be launched on the same server, it wants the Python 3.0, and another want Python 2.6. So we see the problem here, because each of these applications demands from us specific versions of libraries, specific versions of operation systems, specific versions of common runtime environments. Some want some specific version of Java, some work some specific versions of other applications. And if we launch this server number 1 and this server number 2 on the same machine, we would have some very big issues because they would conflict with each other. This Python 2.7 and this Python 3.0, we can have some problems when they would not be able to work with each other, some specific libraries inside them. So what can we do? We have big machine with a lot of cores, with a lot of memory. But if we would like to install more than one server on this machine, we would have a big headache. So the solution before the virtual machine, it was very simple. I would erase everything on this slide. It was very simple. We have a server with some amount of CPU, with some amount of RAM, and we say, okay, this would be the server for the MS SQL server. And MS SQL server would take all this machine. No matter that the effectiveness of this solution would be about 5%. So this machine can handle 20 more of this because it has a lot of power, but mostly it would stand by 95% of the time because the amount of requests to this MS SQL server is not enough to fill all this machine. But we cannot do anything with this because Microsoft SQL Server needs the whole machine. It should work alone because we need some specific environment for this MS SQL Server. So as you can see, 5% of utilization of the server, it is not very good number. No manager in the enterprise corporation would be satisfied if you come to this manager and if you say, you know what, my server works in 5% utilization. He would count in his mind and he would say, oh, so that means that 95% of the energy is wasted. And we would say, yes, of course, we cannot make this more efficient. So that's where the server virtualization comes into the game. What server virtualization provides us? It provides us capability to slice the server in virtually independent parts. And these independent parts, we call them virtual machines. So we have one big server, and we sliced this server on 3 virtual machines: virtual machine 1, virtual machine 2, and virtual machine 3. Each of these virtual machines is working with some part of the server. So these virtual machines have only 2 CPUs and small amount of RAM. These virtual machines have bigger amount of RAM and also 2 CPUs, and virtual machine 3 have only 1 CPU. So what that would allow us to do? These allow us to install MS SQL Server on one virtual machine, install some Nginx web server on another machine, and install our SOAP service on the third machine. What does this mean? That means that the utilization of our machine just risen up from about 5% to about 15%. That's 3 times more effective, because right now our server can handle 3 applications simultaneously. Of course, it is not as simple as that, because virtualization and virtual machines are not so effective working with the hardware as the bare metal installation of the same SQL server. But no matter what, if you use virtualization, you can install more, and the infrastructure becomes more manageable comparing to the bare metal installations. So let's go back to the slide, and as you can see here, the average Windows server load is about 5%, and about Unix servers it's about 10% or 20%. And this approach that we discussed on this slide, one application, one server, does not allow us effectively use the resources of our data center. We would see that our servers are just exponentially growing in the amount. We need more power to work with them. We need more administrators to handle them. It increases the costs for administration, for power, for cooling. We need additional space without the virtualization. So that is where the virtualization comes to save us. At the heart of the concept of the virtualization is the ability of one computer to do the job of multiple computers through the distribution of its resources across multiple environments. As I said, we have one machine and we cut its resources into several independent parts. Virtualization allows distribution of computing resources between applications, each of which sees only its intended resources and thinks that it works on its own dedicated server. In addition, virtualization solutions make it possible to run multiple operation systems on the same machine through emulation of system calls to the hardware resources on the server. So virtualization allows us to launch Linux here, Windows here, FreeBSD here, and one more Linux here. And they would work perfectly on one server using its own resources. Let's briefly discuss the history of the virtualization and where did it come from. As a lot of things in the IT environment, in the core of the virtualization lies the invention of the IBM Corporation. So IBM was the first who thought about creating of virtual environments for different tasks inside a mainframe. And mainframes was the grandfathers of the current server technologies. So in 1967, IBM CP-40 operation systems allowed to create so-called jails, or parts of the operation systems, to separate the tasks from each other. But to the end of 2000s, after the expansion of the personal computers, interest to virtualization weakened, because operation systems applied adequate hardware requirements, and everyone thought, why do I need virtual machine if I can just launch one more server, or launch one more personal computer, or buy one more personal computer? However, rapid growth of hardware capacities in late 90s made it that IT community once again recall virtualization technology platforms. In 1999, VMware, the company that we know very well today, it introduced the virtualization technology for the x86 systems. That is the common architecture today that all Intel and AMD platforms are mostly working with. So later, in the battle for the place for this trendy direction, joined such companies as Parallels, that is very well known for virtualization on the Mac platform, Oracle. When they bought Sun Microsystems, they become the owner of the Java virtualization machine platform. Citrix company developed Xen virtualization technology that is very, very famous in the Linux world. And Microsoft, in 2003, they bought Connectix platform and released their first product, a virtual PC. And now they, if you have Windows 10, you can easily install Microsoft virtualization platform from the components of the Microsoft Windows. So what are the benefits of the server virtualization? First, it is effective use of computing resources. As I told you, we can share the memory and we can share the CPU power of one server between several virtual machines. We can divide it to smaller tasks, and each of these tasks would think that it works on a separate server. Second, it is reduce the cost of the infrastructure, because we do not need to buy more servers if we are able to create virtual machines that fulfill our needs. We reduce the cost of the software, because if we can launch our software in the virtual machine, it is possible to share this software between different users, for example. If you have access to the personal virtual computer cloud right now, you can see that there are some network licensed software platforms that allow, for example, 20 persons work of this platform simultaneously. But if you would install them on separate computers, then each person that would like to use the software need to come to this computer, sit, and work with this software. But if you provide it as a virtual machine, that means that any person from any part of the world can connect to its own virtual machine, launch this software, and work with this. That is great reduction of the cost. It increases the flexibility and speed of response of the system, because incompatible applications can run on the same computer, so it is a very, very flexible solution. It can improve application availability, ensuring business continuity, because we can easily back up our virtual machines. So let's imagine that we have some server solution here. We have a server and we have two virtual machines here, number 1 and number 2. And if we want, we can just copy this virtual machine to our database as a whole. All virtual machine can be copied and stored somewhere in the database. And let's imagine, so right now we have a copy of this virtual machine. And let's imagine some user worked with this virtual machine and it crashed somehow very, very badly and it is not available anymore and all the data is lost, and what can we do? But that is only the issue if we're working with bare metal, because we are working with a virtual machine. The same user said, oh, never mind, just delete this. I would get a copy of this virtual machine, I would install it on some other server, and it would be like new. I would work with this virtual machine in the state where it was backed up. That is great capability. That is a great solution to automate the backup of the applications. And of course, all this leads to improvement of manageability of the computing infrastructure. So let's go to the formal definition of the virtual machine. A virtual machine is a software implementation of a machine or computer that executes programs like a physical machine. Virtual machine is a completely isolated software container that works with its own operating system and applications. Like a physical computer, a virtual machine behaves exactly like a physical computer and contains its all virtual RAM, virtual hard disk, virtual network adapter, virtual CPUs, and all other stuff. But in reality, it is a virtual machine, not a physical computer. Server virtualization means running multiple virtual machines on a single physical server. We can install different operation systems, applications, and services in all of each virtual machines that we have on this server. Typical representatives of server virtualization are such platforms as VMware, for example, ESX Server Workstation, Microsoft Hyper-V, Virtual Server, Virtual PC, XAN, Virtualization. And we already met these type of working with the servers when on our previous lecture we used Amazon Web Services to create us new virtual machine, connect to this virtual machine, and launch on this virtual machine a service that we want. In the core of the virtualization runs a concept of the hypervisor, or virtual machine monitor. The hypervisor takes control of the guest systems. It can be viewed as an abstraction between the hardware platform and virtual machines. Here we can see the hypervisor, where is it located in the concept of the virtual machine. So on the basis of the virtual machine, it is the hardware. It is bare metal. It is what hardware do we have, like physically, RAM, CPU, hard drives, everything that physically we can put or take from the server. On the basics of the hardware runs hypervisor. If we talk about the server, then the hypervisor, it is the only way to distinguish. It is the only middleware software that runs between the virtual machines and the hardware. If we say want to work with the virtual machine For example, on some consumer PC, on the personal computer, then the diagram would be the following. We would have the hardware. We would have our host OS. This is the basic operating system that is launched when the computer is starting. For example, Windows here, or Mac OS. This is host OS. Then we have hypervisor. For example, VMware hypervisor. And on the basics of this hypervisor, we have our guest operation systems. And on the basics of the guest operation system, we have application. So the difference is that if we are working with personal computer, we have some specific host operation system. If we are working with a server, then hypervisor takes the role of the basic operation system. So on this hypervisor, virtual machines are launched and running. Each of these virtual machines thinks that it runs on its own server with its amount of RAM and CPU power. The types of virtualization. So historically, the first type of the real virtualization was the hardware emulation. Hardware emulation means that guest operating system runs on the virtual machine that intercepts every command and simulates it on the real hardware. There is no binding to the host machine architecture, so you can run some not modified operating systems designed for machines with different architectures. For example, you can run ARM operating system on the basis of the x86 processor, because there is no connection to the basic architecture. But this type of virtualization is very, very low performance. It works only if you need to run very, very outdated operating systems or very, very outdated machines. This type of emulation works mostly today. We can see this type of emulation, for example, when we launch emulators of some old gaming consoles. For example, when we want to launch some Nintendo Entertainment Systems games on our PC, we need to launch the emulator that would use the power of our CPU to emulate the Nintendo Entertainment System. Of course, that takes a lot of CPU power, but NES had so low demands for the CPU. It was so slow, it was so not demanding that currently we can launch a lot of emulators of these systems. But this type of emulation and virtualization is not used when we are discussing virtualization of the servers. Next type of the virtualization, it is called full virtualization. To implement full virtualization, we use unmodified copies of guest operating systems. And to support these operating systems, we create a general emulation layer on the top of their host OS. This hypervisor that we provide to implement the full virtualization intercepts only some very dangerous commands, and all the other commands are directly executed on the hardware. So that means that the speed of full virtualization is much higher than the emulation speed, because most of the commands that are considered not dangerous, for example, add 1 plus 2, it would be directly executed on the hardware without the need for emulation. So a lot of platforms are working like this, like VMware Workstation, VMware Server, Parallels Desktop, and etc. But these approach also not very common today, because today, if we're talking about virtualization, the most common way to organize this, it is using Paravirtualization. Paravirtualization approach, it demands our guest operation systems to be modified. So if we use Paravirtualization, we cannot install some operating systems that does not know that it can be launched in the virtual machine. Operating system should know that it works inside the virtual machine, and it should provide some specific API for the hypervisor through which it can operate directly with the hardware without interfering with the other virtual machines. So here we see that we have some operating system, but it is some kind of it is modified to work with the hypervisor, and instead of calling directly the hardware, the operating system knows, oh, you know what, I am working in the virtual environment, so instead of directly calling the hardware, I would use the API of the hypervisor to make this call. That is where the most effective ways of virtualization are going today. And recently they achieved the performance about 98% of the performance of the bare metal operating systems. That is the difference almost negligible. It is not viewable at all. So that is where the server virtualization is currently working with. So such products as VMware ESX Server, XAN virtualization, Microsoft Hyper-V, they all use these Paravirtualization technologies. And almost all operating systems today know that they can be launched inside the virtual machine. Windows 10, Linux, FreeBSD, they all know that, you know what, I can be launched inside the virtual machine, and if I'm launched inside the virtual machine, then I can use the API of the hypervisor to optimize the use of the basic resources. But this is not all, and this is not the most effective way to organize the usage of the server resources. We have one more way to organize it. The OS level virtualization. OS level virtualization uses a single host operating system kernel to create independent operating environments. Each of the guest containers has its own network and hardware environment. In the content of the current way to use the virtual machines and to use the servers, it is the most promising way, and a lot of systems right now are using OS level virtualization. And of course, there are some systems that historically was previously some Virtuozzo, OpenVZ, Solaris containers. But today, mostly, when we talk about OS level virtualization, we talk about Docker container and LXC containerization. So what does this mean? What does OS level virtualization means comparing to the virtual machines previously? So let's take a look on this diagram, and we can see that here we have no hypervisor at all. There is no hypervisor. We have only the basic operating system. For example, Linux. So here, for example, we can use Linux as an example. We just launching Linux, and inside the Linux, we create independent containers. That means that we cannot launch in this operating system like Windows application. We cannot launch here some Windows servers, but mostly we don't need to. Mostly when we use the server, we have a capability to launch a lot of different servers that are based on one operating system. So we can use containers, and these containers, using the common core of the operating system, and on the basis of this core, we can install all the set of the libraries, basic frameworks, middleware that we need to launch the server independently in each container. And each container, it thinks that it works with this operating system independently, that it have some walls between the processes that are launched inside each of the container. But the container, it is not a virtual machine. Container is used to isolate and deliver applications, but not for permanent state storage. So if you remember, I showed that if you have some server and you have some virtual machine here, we can back it up together with all its state, together with all its applications inside and the state of this application. So if we have some database running in this virtual machine and all the state of this database is saved here, we can back up this virtual machine together with the state that is here. That's the very, very easy example. When my laptop crashed when I worked on the department of the system programming, I created a virtual machine from my hard drive. And I launched this virtual machine on the server of the virtual machines in another computer. And this virtual machine of my laptop had all the applications. So I had some games there, and all these games, they were backed up as a virtual machine. Containers are different. When you launch a container, so the container is stateless. It works with the applications, and the processes are running here. So you can look at these containers like a procedure, like a function. Container is stateless thing. To store some information, containers use volumes. And these volumes are external. They are located outside the container. And these volumes, they can be used by different containers simultaneously. So you cannot just go and back up the state in some database, because if you back up the container, the state would be lost, because all the state is located in the external volume. So yeah, your application data usually does not stored inside the container. It is stored in a separate volume that can be used by many different containers. The container does not work with the state. It is stateless at all. So on this slide, we have a comparison between the virtualization and containerization. So virtual machines, such products as VMware, Xen, or KVM, they can launch different operating systems inside the virtual machine. So when you launch the virtual machine starts and loading a basic operating system. So as you boot your Windows, virtual machine that have Windows would be boot as Windows as well. In the containers, they all run the host operation, the OS of the basic operating system of the host machine. In the virtual machine, the isolation, it is very, very easy. It is almost impossible to share files, libraries among the guest operating systems. You need some specific ways to share the data between them. For example, network drives, like you share data between isolated machines. In the containers, it is very differently, because catalogs, they can be transparently shared between different containers. You say, this catalog is a volume number 1, and I want this volume be shared between all the containers. Voila, it works. Image size. It is very different, because when you have an image of the virtual machine and you store it somewhere, it includes the entire image of the base operating system as well. So if you have an image of the Ubuntu server, you store the whole Ubuntu server inside this image, like 2 GB. In the containers, you do not store the image of the core operating system. It used a shared OS kernel image, and that is why it is much less. It only stores images and data about the applications that are on the top of the basic operating systems. Also, it is very, very different about startup time. Virtual machine, it takes several minutes to start a virtual machine, because you need to boot an operating system. You need to boot everything from the beginning. Containers, it takes a few seconds to launch, because you do not need to boot operating system. It boots only applications inside it. So you can boot the container, provide some function, and close it. And it would almost do not take any time. In the contrast, it is almost not possible to boot virtual machine, do some process, and close it, because it would take a lot of time, like 10 minutes only to launch a virtual machine. This is not the only way to organize the isolation of the processes in the operating systems. Containers, they are very, very useful, of course, but we all also know that there is one more way to organize isolation. It is application virtualization. So, as I said, Java provides a virtual machine, and this virtual machine stores each of the application in its separate small container, Java container. When you launch your application in iOS, it also launches a small container to store this application. The difference between these application virtualization and containers is that when we are saying that this application uses application virtualization, one container can hold only one application. When we are talking about virtualization, like containerization, like Docker or LXC, we can have different applications in one container. So that is the difference between the application virtualization and containerization. Last part of the lecture, it is about virtualization platforms. And let's start from the Microsoft Corporation started their virtualization approaches. In 2003, they were some kind of late in the market. They acquired Connectix company that developed the virtual PC solution. And it was transferred to the Microsoft Virtual Server in 2005, 2006. And in 2008, Microsoft provided their own Hyper-V products. And today, Microsoft Hyper-V, it is the basic virtualization solution that is available in the OS of the operating systems of Microsoft Corporation. Next, we need to consider the VMware. VMware is one of the first players on the virtualization platform market, and VMware now is the biggest player on the virtualization platform market. They started in 98 when they patented their virtualization technology, and that was the core of the full virtualization, where they decided, okay, we do not need to 100% emulate the implementation of the OS. We can launch some not destructive and not hazardous commands directly on the basic hardware. So they introduced this concept and they increased the speed of the virtualization dramatically. And since 1998, they were the leaders of the market with their products such as VMware Workstation, that was designed for desktop PCs, VMware ESX Server, that they consolidate physical servers in the virtual enterprise infrastructure, and now they also provide a lot of cloud computing solutions. Citrix, or Xen, Citrix created their Xen hypervisor that was not profit hypervisor. It was a research project at the Cambridge University, and this Xen technology allows the hypervisor to manage the guest operating system using this special hypercall VMI, or virtual machine interface, which requires modifying the core of the guest operating systems. So that was one of the first projects that introduced the concept of the Paravirtualization, and that is why these Xen virtualization platforms was used as the platforms for first cloud computing solutions to virtualize the servers in the cloud systems. Free version of Xen is included in a lot of distributions of the operating systems like Red Hat Linux, Novell SUSE, Debian, Fedora, or other Linux distributions. On this slide, you can see how the Xen virtual machine works. So Xen, it is a hypervisor. You can see it here. And it is working directly on the top of the physical hardware without basic operating system. It starts when the physical machine starts, and it is usually a modified operating system like Linux, NetBSD, or Solaris. So instead of launching basic operating system and afterwards launching the hypervisor itself works as the basic operating system on the top of the physical hardware. That allows to increase the quality of virtualization and the performance of virtual machines. Then afterwards, when this hypervisor launched, it creates guest domains on this machine, and each of these guest domain, it can access hardware devices using this basic DOM0, the basic domain, and using virtualized drivers and cross-domain channels. If you would like to read more about this process, you can go to the description that I provided here in this paper. Another way to organize Paravirtualization, it is a kernel-based virtual machine, or KVM. It is a virtualization infrastructure integrated with the Linux kernel. This hypervisor was developed in 2006, and it relies on hardware support for virtualization that includes loadable kernel modules for Intel and AMD processors. So as you remember, in 2006, Intel and AMD, they provided their processing solutions that natively support virtualization, and almost all processors today, especially server processors, they support this virtualization approach. So KVM use this core virtualization as a basic of its platform. In this virtualization model that is introduced in this slide, virtual machines are created by opening a special device node that have the name of dev/kvm. And the KVM infrastructure uses a slightly modified QAML program to create an instance of the virtual machine. So you can see here that we have a host kernel. It is basically some Linux operating system. And we have guest operating systems, and they access the KVM driver that works on the basis of the QAML program to create an instance of virtual machine and to work with the basic hardware. Each guest virtual machine, it is just a Linux process controlled by the standard Linux scheduler. And inside this process, we can launch different operating systems that are working with the different hardware. Another way to organize the virtualization, as I said earlier, it is containerization. And the containerization today, when you are saying containerization, most of the people would say, oh, that is Docker. But you need to understand that the Docker, it is not a containerization platform. It is not a technology. It is not a technology for containerization. Docker is based on different technologies for containerization, and most commonly Docker used with the LXC containers technology. It is just a wrapper, a very nice and very user-friendly wrapper, a shell for the LXC containerization platform. So then what is LXC? The LXC, or Linux containers, it is a containerization technology that is implemented based on two main kernel mechanisms. First kernel mechanism is used, it is namespaces. Namespaces allows you to separate processes into separate groups. So in our Linux machine, when we start a process, it is going to a pool of the processes that are working together in a Linux machine. Namespaces allow you to say, okay, you guys, you three, are working together and you know about each other, but you do not know anything about these guys who are working nearby. These are not existent for you. You're working together. This is your namespace. This is your namespace. And this is your namespace. And you do not know about each other. You're just separated. So this is OS level separation of the processes. To the root user of the operating systems, all these processes are visible. Root can look at all these processes and see, okay, right now we are working with like 8 processes here. they are launched and they are executing something. But if we are going to log into this namespace, and we would take a look at the list of the processes from the point of view of this namespace, we would see only these 3 processes, and this would be invisible for us. That is what namespaces do. The other thing that is needed to create as a container, it is a control group, or just a second, or C groups. C groups manage and restrict access to resource for process groups by forcefully limiting the processor resources, accounting and isolation, such as limiting the memory available for a particular container. So as I said earlier, we have a set of processes. They are isolated. So this is container 1, this is container 2, this is container 3, and we use control groups to say, okay, you have 2 gigabytes of RAM and you have 1 CPU. You have 1 gigabyte of RAM and you have 3 CPUs. And you have 4 gigabytes of RAM and you have 1 CPU. So this is what control groups does. It provides specific amount of restricted resources to each of these groups. So we have restriction, we have grouping, and we have something that looks like an isolated computing environment. And this isolated computing environment that includes a set of processes and a limited amount of resources of the basic operating system, we call this thing a container. On this slide, you can see how this OS kernel virtualization or containerization is implemented. So on the top, we have our applications that represent the processes that are isolated inside containers. These containers are working inside the container engine, for example, Docker, and we use namespaces and C groups to manage these containers. After we manage these processes and containers, all of these containers are working through the Linux operating system with a basic physical hardware layer. So they share the same operating system kernel, they share the same physical hardware layer, but they think that they have limited resources available only for them. So here you can see this thing, Docker. What is Docker? Docker, it is an open source project that provides automatic deployment of applications with containers. Basically, it uses the Linux container platform, but today you can use different other platforms for implement Docker containerization. It can be run on Linux using Ubuntu, Fedora, any other. It can be run on cloud platforms in Amazon Elastic Compute Cloud, in Google Cloud, in Rackspace. It can be launched and installed on Windows. It is old slide, not boot for Docker. You just go to the docker.com and you install the Docker on your Linux, on your Windows machine. Right now I'm working with Docker on my machine. It is very convenient because when you use Docker, you can go to the repository of different images. So we can go here, Docker hub. Let's go to the Docker Hub, and let's explore what containers can we get in the Docker. We can install each of these containers using just one command, docker run, and the name of the container, the name of the image, and it would be automatically deployed on our machine, and we do not need to do anything about configuration. It would be just launched like an executable file, and that is the magic of Docker. Oracle Database Enterprise Edition. You Docker run Oracle database, and it is launched on your machine. Java, MySQL, Couchbase database, Redis database, Node.js, MySQL, MongoDB, Postgres, MariaDB, what is RabbitMQ, as we discussed. You also can launch very easily. Nextcloud. For example, you would like to create your own small Dropbox just for yourself and your family. You can run a container using Docker run Nextcloud, and it would be installed on your machine. Of course, you need to configure where would it share, where would it store your files, but going deep in the Docker, we would go on our next course next year about the cloud computing solutions. WordPress. If you would like to install your own WordPress on your machine, you can just install it using the Docker. That is the engine that simplifies the process of deployment of enterprise and server applications. So, of course, today, if you would like to have some effective way to manage your server, it can be your home server or enterprise server, you need to know what Docker is. So this is the end of my lecture today. Thank you very much for participation. And as always, in the end of the lecture, we need to pass the final test about the virtualization platforms. I am copying this URL, and you have 5 minutes to pass the final test. Thank you very much for participation.